Welcome to the last talk of the session. I'm Mathé Hertogh from VUSEC, and I'll talk to you about Project Rain, which is about microarchitectural cloud leakage. So this is about the real-world microarchitectural attack that we did. And let's jump straight in because it's a short talk. The threat model we're going to look at is a cloud. We're going to assume we're running on a Skylake CPU with a hypervisor, in our case KVM, on top. And then there'll be two VMs, a victim VM and an attacker VM. The victim VM will be running Nginx web server, and it will have its corresponding private TLS key. And that will be the target that we're going to try to leak. We are going to be the attacker, and what does the attacker VM do? It's going to be running on a core with two hyperthreads, and the two hyperthreads will be running two threads. One will be doing L1TF, also known as foreshadow. This is a transient execution vulnerability in Skylake CPUs, and it allows you to read arbitrary data from the L1 data cache. The other thread will simultaneously be doing half specter, triggering some transient code in the hypervisor, KVM, which allows us to let the hypervisor put any data we want into the L1 data cache. And so combined, this gives us arbitrary data leakage. We did this on real production clouds of both Google and AWS, so Amazon. And today I'll talk about the Google part, because on AWS we gained arbitrary host data leakage. On Google, both host and guest data leakage. So what did we end up gaining? If we combine these two vulnerabilities, L1TF and half specter, we get a leakage rate of 1 byte per second with about an error rate of about 50%. So that's really bad, right? If I put my 62-year-old father in a dark room and I take his reading glasses from him and I give him the newspaper, he can read more than 1 letter per second with 50% error rate, right? So for a computer, this is really bad. But in the end, we did build a, I think, impactful attack with this. So what does the exploit do that we built with this? It starts out like this. We spawn our attacker VM, and we don't know anything, right? We don't know the victim. We just know we're on the Skylake CPU. Then we start pointing chasing the metadata in the host kernel, because the host kernel knows what VMs it's running. And at some point, we'll figure out, there's this other VM co-located with us. And then by leaking some more data, we figure out where its kernel is. And then we start leaking guest kernel metadata to list all its processes, and maybe at some point figure out, it's running Nginx. And in that case, we start leaking the data of Nginx to find its key and leak it. So for example, the Google machine we performed this on had 800 gigabytes of memory. So finding the key is quite hard with the 1 byte per second leakage. But with this pointer chase, we can find it. So now it's time for a demo. I recorded doing this on Google Cloud. It's going to spit out a bunch of stuff. Don't worry if you don't read everything. But so this is a recording where I fast forward the actual attack running in Google Cloud. And as you can see here, it starts out by finding the gadget base. So it needs to find out where this half specter gadget in the host kernel is. Now it found it. And now it's going to try to break host KSLR, basically leaking some pointers and a little bit of root forcing. And once we have that, we need to gain host address translation capability. Maybe it's good to explain this, actually. If we look over here at the top, this is a host physical address. And our leakage primitive is leaking host physical addresses. So then we leak this pointer, PGD. It's a kernel pointer, but it's a virtual address. So I cannot chase it because I only can read physical addresses. So what I have to do is I have to translate to a physical address, and then I can keep pointer chasing. Now, next up is what you see is it's going to spit out all the tasks that are running on the host. So you see a bunch of K workers here. And at some point, it will find the process nanny. That's what Google calls their processes that run VMs. Next up is going to try to find the metadata that is, let's say, attached to that VM. So metadata that we would like to know in order to find its kernel. And maybe nice to show also here, the long line you see that you're actually walking all the page tables. So there's a private data pointer, and then we walk the PGD, the PUD, the PMD, the PTE, etc., in order to keep pointer chasing. So these are the page tables of the host. Next up is we're going to leak the page tables of the guest. That means we need the guest page tables and the extended page tables, so we can start doing two-dimensional page table walks to keep pointer chasing in the guest. So here you see some two-dimensional page table walking to break guest KSLR. It's leaking the swapper process, system D, and then we'll start try to find Nginx. So now it's going to just list the processes that are running in the guest. You see system D, SSH D, Polkit D. The next one is Nginx. Last up, gaining address translation in Nginx. So we take the page tables of Nginx, so we can start reading out each heap. So now we're translating, so doing like a two-dimensional page table walk to figure out where its heap is in memory. And then we can start leaking the key. So now it found like a magic value that surrounds the key, and it will now spit out the key. Let's wait for it. So that's the...
Okay.
Thank you. Maybe this is, if I can have 2 more minutes? Or am I very much out of overtime?
Sure.
So maybe one thing to note, this was actually 6 hours in real time, right? So this was a... sorry? Okay, so let's wrap up the talk. So the results we had on Google were that if we ran this thing 28 times on a bunch of physical machines, 25 of them completed, and 25 correct keys came out. Fully perfect, like every bit correct. Runtime average is about 14 hours. Next up, what happens if you add a lot of noise? So you actually fill up the full system with VMs trying to generate noise. The answer is it doesn't matter. Exploit has the same reliability, same runtime, it works. So I would like to conclude with the message that I think, I hope Project Rain can be a motivating example. I think if you look at the micro-architectural techniques that we guys are doing, then they are quite advanced, they require expert knowledge, they're brittle, like you move to another machine, it doesn't work anymore. They're unreliable, they leak the wrong data sometimes, they're slow, they're inaccurate, and I think this is all true. So, and this is how the rest of the world looks at us, right? The rest of the security community, when they hear about Spectre, they think, yeah, that's slow and brittle and unreliable. Maybe it's not so dangerous. And I think we should take examples like these to show that actually, while these techniques are a bit shitty, the exploits that you can build on top can definitely be very robust, reliable, accurate, reproducible, scalable. Remember, we didn't know our victim, right? You can just spawn 1,000 VMs like this and start leaking keys. Very stealthy. Neither Google nor Amazon ever raised an alert. Well, I've been doing this for like many compute weeks. So I think all in all, this is a realistic threat. So thank you.
Thanks for the talk. Great exploit. So I would have 2 questions. One is like, what is the stability once you basically traverse the pointers into the VM? Does that stay stable, or do you have to re-leak them once you traverse them and a little bit of time goes by?
Yeah, it's a good point, because if you lose the pointer chase, if you leak 1 bit wrong in the pointer, at some point you're gonna lose the track of the trail, right? So I think I actually have even a slide on this. So basically what we do is like this, like every time we chase a pointer, I try to check, so look around in the kernel if I'm still at what I'm thinking is the right spot. And every time I do that, I try to check if it's correct. And whenever I hit an error, so I see something that's inconsistent, then I backtrack and I re-leak that pointer. And even to the extent that sometimes I go back multiple levels, right? So in my page table walk, sometimes I have to go back 25 steps because I made a mistake at the start or something like that. And that's like incorporated in the exploit.
And one more question would be, you traverse the memory of the process now, but probably the key is also mapped in a file. What would you say about traversing the page cache instead, so that you maybe have like less stuff to traverse?
Well, I think that also makes sense. But if you in this case, we first figure out that Nginx is running at all, right? Because if you're an attacker, you don't know at the start what are your victims. So I think if you ever even find Nginx is running, maybe it's quickest to just then look at its heap, because you already found its metadata. But I think you can look at the page cache or so as well. Yeah.
Okay, thanks.
Just one question. So this is a really cool, basically end-to-end chain on Google. Could you explain a bit more what the setup was? So how was this tested? How was this executed? Did you actually spawn a live target and pawn it, or?
Yeah, so what we did is, in front, we talked to all the parties involved, so Amazon and Google in this case, also other clouds, but we never got the bureaucracy right there, to make sure that this was all a priori fixed, right? So it was all ethical. What we did in the end is that the providers, Google and Amazon, told us you can use dedicated hosts, meaning you rent an entire server, a physical server, fully for yourself, and you can deploy VMs on it. And the whole, both software and hardware stack will be the same as if you were running VMs on a shared host. So they said that's a realistic example where if you show it there, it also works in the normal cloud, or like in the shared instances. And so what we did is we took a full machine, we spawned 2 VMs on it, or many with the noise VMs, and we leaked the data from one to the other. So we never had any, it's just for an API that you spawn a VM and get a terminal to it. We never saw anything from the hypervisor or like no debug access or so.
Okay, let's thank the speaker again.